One more time.
All right, so today, or in the next 3 weeks, we're doing the final module for this course, which is trees and tree-based data structures. This is going to be a culmination of a lot of the data structures that we've developed and that we've looked at so far. And we like data structures, emphasis on structures here. The reason that we like data structures is that they have structure, right? And that structure can be exploited for potentially be exploited for efficient operations. The more structure that a data structure has, the more that can be exploited, right? And the motivation here is, as we've seen before, basic CRUD, right? We want a data structure that supports efficient CRUD, retrieval and search, insertion and deletion, and also, updating the other U of CRUD. Right? The CRUD that we're doing with our databases right now, we want the same operations with respect to our data structures, because we need to put stuff in, we need to take stuff out, we need to find stuff. And one of those data structures that we've already looked at is linked lists, right? But we also saw a problem with linked lists. The insertion or deletion, or delete from the head or tail, right? That was an order 1 operation. Now that we've got the language that we can describe this with, big O asymptotic notation here, that was a constant time operation. Because we kept track of the head or the tail, all we had to do was create a brand new node and then link it up, right? There was a constant number of operations with respect to that. But arbitrary insertion or deletion or whatever, or index-based search was going to be order n. And the reason for that was because you had to start at the head and you had to traverse to the one that you wanted. Now, if you just wanted the head or the tail and you kept track of both, then those were going to be an order 1 operation as well. That's why they were ideal for stacks and queues. But if you wanted to access the middle element, that means that you had to start at the beginning and you had to traverse half of the elements to get there. That's going to be order n. That's going to be linear, right? Well, we also looked at array-based lists, right? And we made an immediate observation that these two situations are basically flipped, right? That the insertion or deletion from the start is going to be an order n operation. And the reason for that being is that you have to shift things down or shift them back up on a delete operation. And so that's going to be an order n operation, a linear operation. But an arbitrary index-based search is going to be an order 1 operation, right? And the reason for that is going to be random access. If you are, if everything is stored contiguously and you have the memory address of the first element, and you want the 85th element. All it is a simple order 1 operation to compute the memory offset of that and immediately jump to that memory location. That's what we mean by random access. We also looked at the application of these two in the context of stacks and queues. Right? Both of these offered efficient push, pop, or in the context of queues, we call this pull, offer, or NQ, DQ, right? Operations. But they were restricted access data structures. In other words, they only, structures, right? They were only worked and they were only efficient if you used them as you were supposed to. Only grabbing from one end and inserting at one end or the other or some combination thereof. So they were restricted access. They weren't general purpose data structures where you could arbitrarily put something in, arbitrarily take something out. Structures. Let's respell that. There we go. All right. So our ultimate goal is going to be efficient operations for a general purpose collection data structure. And we're going to set the foundation for this in this module by looking at trees and tree-based data structures because they provide the potential for efficient operations. So today we're just going to look at the basic terminology and why they offer the potential for this. By the end of the semester, we're still not going to be able to get to what are called balanced binary search trees that do offer the ultimate goal here of efficient operations, order log n operations for all operations, but we will get really, really close, and then we'll touch on it, of course. So what do we mean by a tree? Well, this is taken from nature, right? It's really old. I think Cayley is given credit for the first use of trees as data structures like 150 years ago. So what is a tree? Well, a tree is a graph. So we need to start there. A graph is a collection of nodes or vertices. And the reason that we're going to call them nodes is because ultimately data is going to be stored inside of these vertices. In just a general purpose graph, you've got vertices connected by edges, and they've got maybe labels in them, but they're not necessarily storing data. So when a vertex stores data, we call them a node. And edges, right? Connecting nodes. Right? There we go. So let's go ahead and take a look at an example. I'm going to go ahead and just pull up this general purpose graph right here. There we go. Right? So our first observation here is how many nodes are there? 1, 2, 3, 4, 5, 6, 7. Right? So generally we will use the variable n to indicate the number of nodes. N here is going to be 7. Right? This is the number of nodes. Okay. How many edges do we have? Well, I count 1, 2, 3, 4, 5, 6, right? 7, 8, 9, 10, 11, 12, 13, 14, I think. Did I miss any? All right, we'll just say that it's 14. We generally use the variable m to indicate the number of edges. And if I miscounted, sorry. Right? This is going to be the number of edges. Now, if you were in, say, discrete math, or if you were in an actual graph theory course, you would then call G to be a tuple. It is going to be the vertex set along with the edge set. It's a pair of these things. So this is the vertex set, this is the edge set, and so we've got that n is equal to the cardinality of the vertex set, m is equal to the cardinality of the edge set. Don't worry about that because we're immediately going to get away from these graphs and look at more structure. Graphs are great. They're a general purpose data modeling thing. You've seen them all over the place in this semester alone, right? Your UML diagrams are graphs, right? Each class is a node, and classes are connected with these arrows. Your ER diagram is a graph, right? A flow chart is a graph, right? Basically anything is a graph. Why? Because a graph is a way of representing things and the relationship between those things, right? In fact, that's what a graph is. It's just it's a relation, right? So it is used all over the place, not just in computer science, right? How do you I don't know, H2O or H2O? How do you represent that visually? Does anybody know? Like there's an O compound, and then there's two H molecules, something like that. I don't know. These connections between indicate different types of chemical bonds and stuff like that. I don't know enough chemistry to give you an accurate diagram of that. But you can do it, right? Every discipline is going to be able to model some problem using a graph. The problem here is that it doesn't have enough structure yet. This is just a general purpose relationship. What I want is a tree. A tree is an acyclic graph, right? In other words, a graph with no cycles. Right? Now, to understand this, we need a little bit of terminology, right? A path in a graph is a sequence of connected vertices or edges, or nodes, if you want to call them that. A simple cycle is a collection, or is a path that begins, ends at the same vertex. All right? The length of a path or cycle is the number of edges on it. Okay? So now let's take those definitions and visualize them over here with this general graph first of all. Okay? Let's go ahead and get rid of that. I'm going to go ahead and draw a path. I can go from A to E, then I can go from E to F, and I can go from F to C. That is a valid path, right? The path going from A to E to F. What is its length? Well, how many edges did I cross? 3. How many vertices did I visit? 1, 2, 3, 4. What does that tell you about the number of vertices versus the number of edges in a path? Right? It's always off by 1. Okay? Here's another path. I can go from A over to E, over to B, over to G, let's go back to E, right? And then over to F. So let's trace that path. I'm going to go ahead and erase this one here. Right? So if I go from A to E, right, then over to B, and then back to E, and then over to F. That is a path, but it is not a simple path, right? Why? Because it traverses this edge twice here. It goes back and forth. So we're not going to consider those, all right? We're only going to consider simple paths and simple cycles, all right? So this is no, okay? What about another path here? What about A to B to E? Now, is that a valid path? Can I go from A immediately over to B? No. If that edge were there, then I could do that, but this is not a valid path either, right? Because one of those edges is not there, okay? Let's look at another path. Actually, let's get rid of that. Let's go from A to E to G to D to A, right? That's a path, but it begins at A, goes over here, and comes back to A. So that is a special kind of path. What is it? A cycle. What is the length of this cycle? Careful. A to E to G to D to back to A. How many edges did I traverse? 4. How many unique vertices, how many unique nodes were in there? 4. So that the length of this is going to be 4. Okay? That is distinct from the path where you've got 3 vertices. Oh, did I screw up? Uh-oh, sorry. What was the length of this again? A to E to F. There we go. Sorry, what was the length of that? I can't believe I wrote, did I write something else first? I'm not sure. I can't believe I did that, but what is that? That's going to be length 2, sorry. Right? Remember, it's the number of edges on it. A to E to F. So there are 3 vertices here and 2 edges. But down here with this cycle, we've got 1, 2, 3, 4 vertices, unique vertices, A comes back on itself, so it doesn't count twice. But the length here is going to end up being 4. Now let's make sure that I did that one right. A to E to G to D to A. Yep, 1, 2, 3, 4. There we go. So, sorry about that, if I screwed that up. Go ahead and call me on that, or ask questions at least to clarify, right? So, in other words, that graph had a cycle. That's what a cycle is. It's a simple, it's a path that begins and ends at the same vertex. A tree is an acyclic graph, right? So a tree has no cycles. So for example, is this thing here, is this a tree? No, not a tree. Because it has a cycle. In fact, it has many cycles, okay? A to E to G over here. There's another cycle of different length. Here's another cycle involving different vertices entirely, but still of length 3, right, etc. Let's go ahead and take away enough vertices from that tree, or from that graph, to make it a tree. There's the same graph, but several of the edges have been removed so that it no longer has a cycle in it. Right? Now let's do the same counting here. N is going to be the same. There are going to be 7 vertices here, 7 nodes, right? 1, 2, 3, 4, 5, 6, 7. How many edges are there? Now it's much easier to count because it's a much simpler diagram. 1, 2, 3, 4, 5, 6. Ooh. What does that tell you about the relationship between the number of vertices and the number of edges in a tree? So my first observation here. Let's make some observations. Observations. For a connected tree with n vertices, there are m equals what edges? N minus 1, right? N minus. Why can't there be n vertices? Let's go ahead and try. Let's go ahead and try it with a graph of just 1, 2, 3, 4 edges here, or vertices. If I try to 1, 2, 3, try to add just one more. What could you add? Well, you could add this one, but guess what? There's a cycle there. You could add this one, but guess what? The entire thing becomes a cycle. Right? In other words, if you add just one more, you will induce or create a cycle. Okay? All right. You can have what are called disconnected trees. For example, let me go ahead and add this one, add this one, add this one, and then another one over here, and then an isolated vertex over here. How many vertices do we have here? 1, 2, 3, 4, 5, 6. How many edges do we have? 1, 2, 3. So it doesn't follow that convention anymore that it's n minus 1. But that's because it's disconnected. It is a collection of trees. Here's a tree, here's a tree, here's a tree. Right? You can have a tree of one vertex with no edges, right? This is called an isolated vertex. Or somebody suggested one year that we call it a seed, right? Because it eventually grows into a tree, right? And this entire thing is called a forest. When you have more than one tree, it's a forest, right? We're not getting fancy with any of this terminology here. We're just stealing from nature, okay? All right, so there is our tree. Now, so for a connected tree with n vertices, there are that many edges. A disconnected tree is called a forest. Right? It could be, but it still has no cycles. What other observations could we make here? Right? Let's go ahead and fix 2 vertices. Okay. Let's go ahead and say A and G. So from now on, we're only going to consider connected trees. We're not going to consider forests. Everything is going to be connected because, again, why do we want to do this? We want structure. We want rules that are not violated so that we can expect those rules to exist and exploit those rules for efficient data structures and algorithms. What about A and G? How do I go from A to G? Do you see the path? I go from A to F, and then I go to C, then I go to G. Now, this is an undirected graph, so all of these paths are going to be unoriented. You could start at G and then go back to A. Right? That's the same path. Going from A to B to C, and then C to B to A, that's going to be the same path. First of all, what is the length of that path? It's going to be 1, 2, 3 is what I count. Okay. Now, is there going to be another path from A to G? Remember, forwards, backwards, it's the same path. Is there going to be another one? Suppose there were. Suppose that there was this magic path here that went from A to G, independent of these edges over here. Tell me about this tree now. Is it a tree? No, why? There, and then follow it back, and you've got a cycle. Right? So my second observation here is that between any two nodes, there is exactly one unique path. Between any two nodes, there is exactly one path. Because again, remember we're talking about non-disconnected trees. We're not talking about forests. There's always going to be a path from any vertex to any other vertex, right? Excellent, okay. Now we need a little bit of orientation here, right? Orientation. Trees can be oriented, right? And to do that, what I'm going to do is I'm going to come over here, and let's go ahead and erase all this stuff. And I'm going to ask you to imagine that this is not written on a flat piece of electronic paper here. What I'm going to ask you to do is imagine that you took a vertex and you picked it up off the paper, and then you dangled all of these vertices off of it, right? You shook it so that you let gravity take it over, and all of these nodes would then be hanging off of this node. What would it look like if I did that from A? Okay. I would have D, E, and F hanging off of it. Okay. Well, off of D, do I have any other vertices? No, so that's the end of it. Off of E, do I have any other vertices? Nope, that's the end of that. But off of F here, I have additional vertices hanging off of it. I've got C hanging off of that, I've got G hanging off of that, and I've got B hanging off of that. So again, if you imagine that you pulled this out of the paper, you dangled it, and shook it out so that gravity took over, that's what the orientation would look like. Up here we've got the top of the tree, and down here we've got the bottom. Right? In computer science, our trees grow downward. This thing up here is called the root. Right? Any vertex that doesn't have any descendant nodes, right, is going to be called a leaf. Right? This is also a leaf. What about the rest of them? Well, sometimes we refer to those as internodes, but they're not leaves, they're not roots, who cares, right? We've got leaves here. Why do our trees grow downward? If you go back to the original paper 150 years ago, Cayley's trees also grew downwards. Why? Because he envisioned them as holding data. He envisioned them as holding at least labels or numbers or something like that. And we, at least in English, we read top to bottom, left to right. So our trees are always going to grow down, right? That's not the only kind of tree that grows down. Think about a family tree. You've got your descendants up here and your ancestors up here and your descendants down here. Where are you in that tree? You're down here at the bottom. You're a leaf until you have children, and then you become an internode, right? Is there any root? Well, you go back as far as you can, and then that's where it ends. That's where the root is. Right? That's not the only orientation that we could have had. What's an alternative orientation here? I just started at A because lexicographic order. What if instead I had done C? Right? Pull C out of this piece of paper, this electronic paper, and dangle it off. And I've got F, and G. There we go. Off of G is hanging B. Off of F is hanging A. Off of F, A is hanging D and E. And then I'm missing B. Oh, no, did I get everybody? I think I got everybody. D, E, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, I got everybody. Right? And this is looking more like a tree that we like, which is called a binary tree. Right? Trees can be oriented top to bottom, bottom, left to right. Right? At the top is a single node called the root. Right? This induces a parent-child relation. Right? And you can also talk about ancestors, descendants. Right? It likes it that better. You can also use things like, cousins and uncles and nephews and stuff like that. Grandparents, grandchildren. You can use all of the terminology that you would have from a family tree when you're talking about our trees, right? So suppose that we have a further restriction here, right? So suppose we add even more structure. That for any node, there can be at most 2 children. So that first orientation we had, where A had 3 children, that's not what's called a binary tree. But this orientation, right, is a binary tree. When we say child, of course, we're looking at F here. Its parent is C. Its child is A, and it only has 1 child. But if you look at A, it has 2 children. Okay. G has 1 child. B doesn't have any children, right, because it's a leaf. So this is a binary tree because we have restricted it so that there are at most 2 children. There can be 0 children, there can be 1 child, there can be 2 children, but there can't be 3 or more children. Okay? So this restriction is known as a binary tree. Such a tree is a binary tree. And why binary? Because base 2, 0, and 1, that's a reference to that, right? In a binary tree, you can have 0 children. This is a leaf, right? 1 child or 2 children. You can further orient these left to right, further structure. We will orient the 2 children to left and right. So I didn't draw it like this, right? Because I drew A right here down immediately as a descendant here. Likewise, G down here. But I could have drawn it differently. What I could have done is I could have drawn it like C is still going to have a left child, which is F, and a right child, which is G. Now I need to pick. Is A going to be a left child or is it going to be a right child? I'll just go ahead and make it a left child and skew it a little bit here to the left. Okay? And then it, of course, has 2 children, D and E. For my child over here with B, I'll go ahead and make that into a right child. So again, F has 1 child, its left child, but it does not have a right child. G has a right child, but no left child. And D, C, and B here, they have neither child, they're leaves. Okay? Once we've got that orientation, we've got a lot of structure here to work with, right? We still need a little bit of more terminology, right? Terminology or definitions. Right? Now that we know what paths and cycles are, well, first of all, we know that there are no cycles. But if we look at the paths in a tree with respect to the root node, then that gives us what's called the depth of a tree. Let me come over here and let me give you a more complex tree, just so that we have something to work with. Binary tree. There we go. Here is a much larger tree. And again, E has no left child, but it does have a right child. A has both children. R has no children. It's a leaf. What's another example? M here has a left child, but no right child. Right? So now what we can do is we can look at each one of these nodes, and we can determine what's called the depth of that node. Now remember, our trees grow downward, so the depth here is going to be down here. Okay? Let's immediately jump here to B. Oops, I'll just write it as B. What is the depth of B? The depth is defined as the length of the unique path from the root node to that node. There's the path. There's only one, and it's unique. And it's guaranteed to be there because this is not a forest. It is a connected tree. So, the depth here is going to be 1. Well, guess about what the depth of C is. Right? Also 1. Why? Because I drew them on the same level. Okay? Anything on the same level is going to have the same depth. For example, H here. There is a unique path going from A to B to D down to H, right, of length 1, 2, 3. And it's going to be at depth 3. Everything here is going to be at depth 3. So D, E, and F, they're all going to be of depth 2. What's the next level? H, G, H, I, J, and K. They're going to be at depth 3. Then L, M, N, O, P, Q are going to be at depth 4. And down here by itself is going to be R at depth 5. I left a little room up here for A. By convention, what is the depth of the root node here? Remember, this is the root. Well, what is the length of the path from A to itself? Well, you're already there, so by convention, it's going to be 0. Okay? Now, the depth of the tree itself, is going to be the maximal depth of any node. In other words, you want to know how deep, at most, worst case scenario, how deep do you have to go into this tree to get to the most furthest away node when you start at the root? Right? Well, in that case, it's going to be 5. Right? If we had erased that, I can erase it by doing this, right? There we go. If that node was not there, then the deepest node now would be L, M, N, O, P, Q, right? And so the depth of the tree would now be reduced to 4, okay? But that's not what we have here. We have a depth of 5. All right, so some terminology definitions here. The depth of a node, U, is the length of the unique path from the root to that node. Right? By convention, the depth of the root is 0, right? And the depth of a tree itself is the maximal depth of any node. And we say maximal here because, again, if I had erased R here, there are multiple nodes here at depth 4, right? And so we can't say maximum because there's 1, 2, 3, 4, 5, 6 different nodes at that maximum depth of 4. Right? So that's why we say maximal instead of maximum. Right? All right, excellent. So now that we have this structure, how can we exploit it? Okay. Generally, we will store data in each node. Operations such as search, insert, delete will always begin at the root node. This is very similar to a linked list. We didn't keep track of every single node in a linked list. If you kept track of every single node in a linked list, guess what? You've got an array-based list. So we're not going to go that path. Instead, we're going to just keep track of the root because everything is going to be with respect to that root, right? And if, my observation here is, if we can define operations such that, with efficiency, proportional to the depth, we may be able to make them very efficient. Right? So if I can go ahead, if I can define an operation that is searching for a node and it's proportional to the depth, right, and that depth can be made efficient, then we've achieved our ultimate goal here of making a general purpose data structure with all efficient operations. Just as a preview here, if you're searching for something, right, you start at the root and you say, well, okay, which area of the tree should I go to next? I could go left or I could go right, right? If you are sure that the thing that you're searching for, if it existed, would be in the left half of this tree or the right half of the tree, what have you basically done? You've cut out effectively half the tree. Gee, that sounds familiar. Where have we seen something like that before? Binary search, right? Binary search trees is what we'll eventually look at here. Before we do that, though, I want to understand, and then I guess why would it be proportional to the depth? Say that we're searching for something and then we get to the end of a tree. Right? We're done. We either find it somewhere up here or we get to the end of the tree and say, oh, it doesn't exist. The depth here, if our operations can be proportional to the depth, then we've achieved our goal. Why is the depth important? All right, what I want to do is I want to look at this from the perspective of a full binary tree. And what I mean by full binary tree is that at each level, every single node is present. That's not true over here. E does not have a left child. C does not have a left child, and therefore this big giant tree here, there we go, that would be otherwise be hanging off of this, doesn't exist, okay? But if I assume that it is a full binary tree, then what is its depth with respect to the number of nodes in it and vice versa? So to do that, let's go ahead and draw it out and see if we can discern a pattern here. So this is going to be the root. This is the depth of 0. And how many nodes do we have at this depth? Number of nodes. Well, if it's just one node, then it's pretty clear that there's only one node. Now let's go down one depth, where we've got 2 children here. This is a depth of 1. And there are 2 nodes at that depth, a total of 1, 2, 3. Okay, we'll worry about the total here in a bit. Let's go one more. 1, 2, 3, 4. At depth 2 here, we've got 4 nodes. I don't want to have to draw too many of them, so you tell me, ... At depth, say, K? Yeah, let's go with K, ... How many nodes are there going to be at that depth? So what is the relationship between these two numbers? It's going up by powers of 2, right? And there's your power right there. Right? So this is 2, here, I'll write it out explicitly. This is 2 to the 0. This is 2 to the 1st. This is 2 to the 4th. So therefore, this would be 2 to the K. There we go. Now, if I went all the way down to, say, depth D, right? This is the depth of the tree, then how many nodes are going to be at that depth? 2 to the D. So my question is, what is the grand total? If I added all of these up. If I said 1 plus 2 plus 4 plus 8 plus ... all the way up to 2 to the D. That's going to be a summation of K running from 0 up to D of 2 to the K. All right? Again, that's going to be, when K is 0, then it's going to be 2 to the 0, which is 1, plus 2 to the 1st, plus 2 to the 2nd, plus ... plus 2 to the D. Okay? That's my summation, that's my series here. Okay? And it's a finite series. What is that? Anybody remember that? Powers of 2? Or in general, if you go with x to the k of k equals 0 up to d, right? This is going to be x to the d plus 1 minus 1 all over x minus 1. Right? That's just a closed form for that series if you've ever seen that before. Our x here is fixed though. What is our x? 2. So what happens when you plug 2 down here in the denominator? Goes away. 2 minus 1 is 1. What happens when you plug 2 up here? You get exactly what we're looking for here. 2 to the d plus 1 minus 1. And then the denominator goes away. You won't need that general purpose one there. This is all we're interested in. Okay? So my values here, where n is equal to the number of nodes in a full binary tree of depth d, is equal to 2 to the d plus 1 minus 1. Now, why is that important? Let's look at it from the other perspective. Here's the next question, right? Given a tree with n nodes, what is its depth? D with respect to n. Remember that n is equal to 2 to the d plus 1 minus 1. In other words, the question I'm asking here is solve for d. Okay? That means that we'll take the minus 1 onto the other side. I'll have n plus 1 is equal to 2 to the d plus 1. Okay? How do I get rid of that 2? Log. Log of, and then don't lose your parentheses there, is equal to d plus 1. Right? Now what happens to that plus 1? Take it onto the other side, and we either got that d is equal to log of n plus 1 minus 1, or if you just ignore those plus minus 1s, what is it going to be? Order log n. That looks super familiar too. Where have we seen the performance of a log of logarithms? Binary search, right? And it makes sense because if you look at an array that is sorted, right, and here's the middle element, and here everything over here is less than m, and everything over here is greater than m. Think about binary search. You start in the middle here, and then you either traverse left or you traverse right, depending on whether or not the thing that you're searching for is, well, if the thing you're searching for is m, you're done. You got lucky. Right? But if the thing that you're searching for is less, then you effectively come over here, or you effectively go over here. Reorient that so that m is not in an array. Instead, it's a little node sitting up here. And off of that node, you've got an array hanging over here and an array hanging over here, such that everything over here is greater than m, everything over here is less than m. Right? What's to stop you from continuing that? Right? So instead of an array here, we'll go ahead and cut it down so that there's an x here. Everything over here is less than x. Everything over here is greater than x. Right? So what can you do now? Replace this with another node with things hanging off of it. All we've done here is reoriented an array that is sorted into a tree structure. Right? And if it's well balanced and half the things are over here and half the things are over here, then we might be able to simulate the same performance of a binary search without requiring random access, that everything be stored in the same location, all in a contiguous location. In other words, we might be able to get the best of both worlds up here. The things that linked list offered, efficient, insert, delete at the head or tail, not exactly constant, but pretty darn close. And then all of the things that were efficient with an array-based list, searching and sorting in order log n instead of linear time here. Right? And that's why we really like these trees here. But we need a little bit more structure first. Okay? Before we do that, let's take 5 minutes here and envision how we could implement this in Java. I'm going to go ahead and create a new class to represent a binary tree node. And I'm immediately going to parameterize it. Why parameterize it? Because you're going to be holding data in this binary tree node. And what type of data are you going to hold? You're going to hold elements of type T. This is going to be looking very, very similar to our linked list, by the way. Right? What do I keep track of now? And with a linked list, I kept track. I don't want public, sorry. Private. Private node T next. Right? Because you only went one way. But we're not going one way anymore. Now we're going two ways. So let's go ahead and, well, correctly spell private first. Binary tree node, it's not just next. What is it? Remember, we oriented this stuff into a left child and a right child. There we go. Excellent. By the way, if you're wanting for some convenience here, right? Let's take a look at this tree again. If you want some convenience here, you can always go down to the left child or down to the right child. But what if you wanted to go the opposite direction, like a doubly linked list, where you can go one direction, but then also the other direction? Go up. What would we call that guy right there? Not a child, but it's just the opposite direction. It's parent. There we go. There. There's the beginning of a nice binary tree node. That's just one of them, right? Let's go ahead and create a new class to represent a binary tree. And again, we're going to parameterize it immediately because we learned our lessons when we did linked list and array-based list implementations. Always parameterize it so that you have one implementation for any type. Now, am I going to keep track of every single node, public list, or not public, but private list of binary tree node of whatever types, right? All of them. That doesn't sound right to me. If it's a list, it's a list-based data structure, right? You only want to keep track of one of them. Which one do you want to keep track of? The root. Because that's where everything is going to start. You always start at the root, and then you go left or right. Why would you start at an arbitrary inner node here, right? Why would you start at an arbitrary leaf? Right? There's only one thing that's oriented way at the top, the root. Right? That's what we're going to keep track of. Okay? You probably also want to keep track of, just like a linked list, anytime you add something or remove something, you increment, decrement the private int size. Right? Now let's make the, let's see. Yeah, let's go ahead and make a constructor here. This dot size is equal to 0, and this dot root is equal to null. Yeah. All right. That's a pretty, we don't have a bunch of getters, setters here. We'll eventually want those. But now we need to start asking ourselves, how do we get stuff into this tree? How do we retrieve stuff from this tree? How do we remove stuff from this tree? The basic CRUD, create, retrieve, update, and destroy for a data structure, right? And that's going to take a little bit more foundation to get that started. But we could stub it out, right? Public void insert an element item. I'll just call it X. There we go. To do. There's an insert. Now, would it make sense to insert at the head or at the tail? No, it's not oriented like that. It would make sense to insert as a leaf, maybe. It would make sense to insert as new root, right? Those are all leaky abstractions, right? Here's a data structure. I want to put stuff in, I want to take stuff out. I don't care if it's a binary tree, I don't care if it's a linked list, I don't care if it's an array-based list. I want to put stuff in and I want to take stuff out. Right? Insert at a particular location, or as a root, right? That tells me that it's a tree. I don't want to have to worry about that crap. I just want to use this as a data structure. Insert. That's not a leaky abstraction. Something to think about when you're designing your list for not this Friday, but the next Friday, right? Does it make sense to have a public void insert at index tx? Well, does it make sense here with a tree? Are there indices in a tree? Doesn't make any sense. Does it make sense for your sorted list class? Here's 10, here, let me come over here. Here's a nice sorted list, 10, 20, 30, 40. Should I be allowed to insert 42 any old place that I want? Oh, go ahead and insert it at index 1. Oh, go ahead and insert it at index 1, 2, 3. Does that sound like a sorted list to you? Then it would be what? An unsorted list, just a regular old list. Right? So when you're designing your interface, make sure that you're reading those common pitfalls, because supporting something like this is going to be huge points off. Right? And I've said it in class explicitly. It is in the assignment explicitly. Do not do that. This is exactly what you should be doing. Insert it. I don't care where you put it. That's your job. You're the sorted list. I don't care where you put it. You're the tree. That's your job, right? Not my job. Right? Anything else would be a leaky abstraction. Okay? All right. I'll see you on Wednesday for more.